Now we will prove this property t for any t greater or equal to 0 for a Wiener process. W squared t minus t and wt are martingales. So we are in lecture 3, so let's prove this. So we know from the properties of Wiener process that expectation of w squared t is t, right? Now by Jensen inequality, we have expectation of wt, modulus of wt is less or equal to expectation of wt's square to the power half, right? And that is equal to square root of t, and which is less than equal to infinity, right? So w2 is integrable, which is the first property of marting to be a martingale, a process to be a martingale, right? And since wt minus ws is independent of the sigma algebra fs for t greater than s, we have, make sure you understand why this is, okay? When we have expectation of wt given fs, this can be written as wt minus ws plus ws given fs is equal to so this is expectation wt minus ws, unconditional expectation of wt minus ws, because this is independent and ws is fs measurable, so this is simply ws. So now this is 0, right? Because we know from the property of Wiener process that expectation of Wiener process is 0. So this is this is 0, this is 0, so this is simply ws. So we have proved that wt is martingale. That's the last property of the wt to be a martingale, right? So conditional expectation of wt given fs is s, and for all t greater or equal to s. Now we have to prove that w squared t minus t is also martingale. Let yt be w square t minus t. Okay, now expectation of modulus of yt is equal to expectation of modulus of wt square minus t, which is less than equal to expectation of wt square plus t, which is 2t strictly less than infinity. So yt is integrable. Yt is integrable. Now using property of conditional expectation, we see wt square given fs is conditional expectation of ws plus wt minus ws square given fs, right? And this can be further written as ws square plus 2 ws wt minus ws plus wt minus ws square given fs, right? Now this is can be further broken into expectation, conditional expectation of ws square given fs plus 2 times conditional expectation of ws wt minus ws given fs plus conditional expectation of wt minus ws square given fs, right? Now this is ws is fs measurable, so this is simply ws square, and ws is fs measurable, so we can take out ws, and wt minus ws is independent of independent of the sigma algebra fs, so we can write this as an unconditional expectation of wt minus ws, which is 0, we know from the property of Wiener process, and this is also same independent of ws fs, so this can be written as simply wt minus ws square, unconditional expectation of that. Now this is ws square, this is 0, so this is 0, and this is t minus s, right? So finally we get ws square plus t minus s. So look, this we finally get this. So w expectation of yt, which is w squared t minus t given fs, is expectation of w t square given fs minus t, which is equal to ws square plus t minus s square minus t, which is equal to w squared s minus s, which is